Hi everyone, welcome back to Math 261. This is Scott. Let's get started. In the last section, we saw some of the magical properties that orthonormal bases might have for a vector space. What we're going to do now is look at the procedure that we can use to make an orthonormal basis for a vector space. So this is what's called the Gram-Schmidt process. So 6.4 gram, that's gram, not like a graham cracker, but gram spelled the same way as the unit of measurement. Gram-Schmidt process. So the idea here is that we are going to have a subspace W with a basis, and we're going to make an orthonormal basis out of that. So Gram-Schmidt process. So the idea. Given a subspace W of Rn, we can make an orthogonal basis and an orthonormal basis. And here's how we will be proceeding. So here's the setup. The setup. W has a basis that is not orthogonal, not orthonormal, not anything great, just some random basis. Let's say it's x1 to xp. So there's our setup, and we are going to be making. We're going to bootstrap our way up to an orthogonal basis, recycling at every stage the x's that we have here, and we're just going to be taking orthogonal complements in order to produce things that are orthogonal to everything that has preceded. So we're going to make an orthogonal basis out of this by, and first we'll describe it in words, and we'll see what it means in math, and then we'll do it as an example. By 1, starting with v1 equals x1. So that's our first element. We're just going to take the very first element of the original basis, and we'll just accept that for what it is. And then 2, add new elements by taking the orthogonal complement of the next xi with respect to all of the preceding no, actually that's only 1e there. I always get preceding and proceeding mixed up. They're actually from the same Latin root, so it's a little bit inconsistent that in the English spelling one of them is done with 1e and one of them is done with the other. With all the preceding v. Say v's. Okay, so what does this actually look like? So what this means is, so v2, what we're going to do is we're going to take x2. So we would have just been able to take that, but what we have right here is not orthogonal to the already chosen v1. So what we do is we will take the orthogonal complement with respect to that, so that it will become orthogonal to the preceding v1. So then that becomes x2 dot v1 over v1 dot itself times v1. And that's good for v2. And then if we want v3, well, we would want to take x3. However, we can't just take this. It's not orthogonal to the preceding v1, and it's not orthogonal to the preceding v2. But we can make it orthogonal to them by taking the orthogonal complement. So that's going to be x3 dot v1 over v1 dot v1 times v1. So that now makes it orthogonal to v1, and we continue our orthogonalization by making it also orthogonal to v2. This will be x3 dot v2 over v2 dot v2 times v2. And it will proceed accordingly. So then if we wanted to go down, let's say vi is equal to xi minus, and then here we would have xi minus, or sorry, dot v1 over v1 dot v1, and it'd be minus a whole bunch of, times v1. Maybe minus a whole bunch of terms like this until we got to the penultimate one, which was, or the last of these, which is the one just before I. So that'd be I minus 1. So it's x I dot v I minus 1 over v I minus 1 dot v I minus 1 times v1 v I minus 1. Okay. So this gives us now an orthogonal basis. If what we wanted was an orthonormal basis, then you would just scale each of the vectors down until they were all unit vectors. To make the basis orthonormal, scale each vector to produce a unit vector. So in particular, ui would equal just vi divided by the magnitude of vi. All right, let's try this. As an example, make an orthogonal basis for the column space of, and let's just say A, which equals 1, 2, 0, -3. Then let's say 1, 1, 1, -1. And then let's say 0, 2, 1, and then 3. Alright, so here what we've got is a matrix. It has 4 rows, 3 columns, and the column space of it then would belong to R4, be a subspace of R4, and this would be a basis for the subspace. So let's see. So that means then X. So this at X, which is equal to X1, X2, X3. So this is our original basis, capital X. With it's common to write those in order to distinguish it from like the times or something like that. And that's equal to 1, 2, 0, negative 3, 1, 1, 1, negative 1, and then 0, 2, 1, 3. And if you were in any kind of doubt as to whether this was linearly independent, you would want to make a quick check of that. So you could do a row reduction, or you could find, I actually can't find the determinant because it's not a square matrix. So you can find a row reduction and confirm that it is in fact linearly independent, but I claim that it is. And one way you can see that is this third one couldn't be any linear combination of the first two, because this and this would imply that they'd have to be opposites of each other, and this implies that that basically this one will have to be equal to 1. There have to be a weight of 1 on this one, and so that would make a negative 1 for this one, and that just isn't going to work out. Okay, so they are linearly independent of each other, so they are a basis, but they're not an orthogonal basis. Well, let's start. So the very first element of the orthogonal basis is going to be just x1, which is just going to be 1, 2, 0, negative 3. Alright, so we have started by just adopting the first element of the original basis as the first element of our eventually orthogonal basis. Now for v2, that's equal to x2 minus x2 dot v1 over v1 dotted with itself times v1. So this is equal to 1, 1, 1, negative 1, minus. And then on the top, it's going to be x2 dot v1. So it's going to be 1 times 2. So it's going to be, 1 times 1 plus 1 times 2 equals 3, plus 3 equals 6. And then downstairs, what we're going to have is v1. Oops, wrong thing. No, that's right. And then downstairs, we're going to have v1 dotted with itself. So v1 is this. So it's going to be 1 squared plus 2 squared plus 3 squared, and so that equals 14. And that's times 1, 2, 0, negative 3. Now, if we wanted, so this is the same as 3/7 by the way, so that's 1 minus 3/7 is going to be 4/7. It's going to be 1 minus 6/7 is 1/7. And here we're going to have just 1, and then here we're going to have negative 1 minus 9/7. So negative 1, actually I guess plus 9/7, so that's going to be equal to negative, it's going to be equal to 2/7, I believe. And if we wanted, we could scale this up if we desired. So note, to simplify, the arithmetic, we can scale the VI to clear fractions. And that's perfectly fine because we're just going to end up scaling them all anyway to make an orthonormal basis if that's our goal. And so we can scale this to clear the fractions and get V2, in fact, of 4172. And now for the last V3, we take as our starting place x3 from the original basis, but it is not currently orthogonal to the previous v's. So what we do is we take this and we subtract the orthogonal complement, or we subtract the orthogonal projection onto the previous v's. This is going to be x3 dot v1 over v1 dot v1 times v1 minus x3 dot v2, so the one we just found, that version, over v2 dot v2. Now you could do this with still the fractional versions of the v2, but there's no advantage to it because we are suspending all our scaling until the very end, and scaling this up or down in the meantime doesn't change its fundamental relationship with the other vectors. It is still linearly independent and is still in fact orthogonal to the rest of them, and so it's not going to have any material effect on anything. So let's see what this would be in this particular case. So x3 was 0, 2, 1, 3 minus. Alright, so x3, that's this one, dot v1, that's this one. So it's going to be, looks like 4 minus 9, it's going to be negative 5, and then divided by v1 dotted with itself. So that was, well, we already calculated that, that's 14. Okay, and then that's times v1, 1, 2, 0, negative 3. Alright, and then minus again, what we have here is going to be x3, that's this, dot v2, so we'll be using this one. So it's going to be 0, 2, 7, 6. So that adds up to, I believe, 14 divided, oh wait, sorry, let me check that again. 2 plus 7, no, 15, I mean 15. 15. So it's going to be 15 divided by v2 dotted with itself. So it's going to be 16 plus 1 plus 49 plus 4. So 49 plus 1 is 50, 66, 70. Alright, and then that's times 0, 2, 1, 3. So just as a note, these have a common factor of 5, so it's going to be the same as 3/14. Okay, so going across on the very top, we have 0 plus 5/14. So that's going to give us this is times v2. So it's going to be 4, 1, 7, 2. All right. Okay. Oops. That's why pencils have erasers. Fountain pens, however, don't. Okay. So it's going to be 5/14 minus 12. 12/14. So it's going to be 5/14 minus 12/14 is going to be equal to 7/14, negative 7/14, which we'll deal with that. Deal with the obvious common factor there when the time is right. Don't want to pile too many things on my already precarious arithmetic here. So we have 2 plus 10/14 minus 3/14. So it's going to be 2 minus, so plus 10/14 minus, so it's going to be 7/14. So it's going to be 2.5. So 2 plus 10 minus, yeah. So 2.5. So in other words, 5/2. All right, and what do we have here? 1, that's 0, that's nice. And then 7 times, so this is going to be 3/2. So 1 minus 3/2 is -1/2. And then lastly, you can use a calculator for this to calculate it or to check it. And then lastly here, what we've got is 3, we've got minus 15/14, and then plus minus 6/14. So it's going to be 21/14, which is 1.5. So 3 minus 1.5, which is going to be 1.5. So this is equal to -1/2, 5/2, -1/2, 3/2. Just a second, check that. Okay, I just did a check with a calculator, and sure enough, it checks out. And if I want to scale that, then V3 can be scaled up to be -1, 5, -1, 3. All right, now that's the first question. Now, create. An orthonormal basis. Out of the above. Okay, well, U1 is equal to V1 divided by the magnitude of V1. So U for unit, which is going to be, so V1, we already calculated V1 dot V1, it's 14, so it's going to be 1 over square root of 14 times 1, 2, 0, -3. And that's then going to give us 1 over square root of 14, and again, we are not going to worry about rationalizing denominators or anything like that in this class. 0, -3 over root 14. U2 is equal to V2 over the magnitude of V2. And so that's going to be, what did we do? We already calculated this, and it was 70. So 1 over square root of 70 times V2, which was 4,172. That's 4 over root 70, 1 over root 70, 7 over root 70, and 2 over root 70. And then finally, U3 is equal to, so now it's going to be V3 over the magnitude of V3, just by the standard business here. So this is going to be 1 over the square root of, and this one I haven't calculated yet, so it's going to be 1 squared plus 5 squared plus 1 squared plus 3 squared, so that's going to equal 10, 35, 36. So that's going to make a total of 6, or so square root of 36 is going to make 6. Oops, negative 1, 5, negative 1, 3. And so that's going to equal negative 1/6, 5/6, negative 1/6, and 3/6, or in other words, 1/2. Of 6, negative 1/6, and 1/2. All right. Now, one of the reasons why we might want to make an orthonormal basis for out of a matrix, the column space of a matrix, is that we can use that to do what is called the QR factorization. And here's how it works. So setup. If A is m by n with linearly independent columns, then A can be written uniquely in the form A equals QR, where Q is an orthogonal matrix, meaning, if you remember, orthogonal matrix means it has orthonormal columns. And R is an upper diagonal, or sorry, upper triangular, I should say. Upper triangular matrix with all positive entries along the main diagonal. So not 0, not 0 and not negative. Alright, so here's a recipe for making the Q and R. Recipe for Q. First, use the Gram-Schmidt process to find an orthonormalization of the columns. So use the Gram-Schmidt. to get an orthonormal basis for a column space of A. So this will be the first draft. This will be the first draft of Q. Will be the matrix we make out of this. So use these vectors for Q. Then, so this is the first draft of Q. But then we may have to modify it, and here's how we get the Q. Or get the R. So recipe for R. So if A equals QR and Q is orthogonal, so these, so A equals QR and Q is orthogonal, which means Q transpose times Q equals the identity. If Q is a square matrix, then that means Q itself, that Q is its own inverse. So Q transpose is its own inverse, but maybe it's not square, so then we don't really necessarily say inverse. So Q transpose times Q equals I. So that means that Q transpose times A is equal to Q transpose times Q times R, which means then that that over here we have just the identity, which makes just R equal to Q transpose A. Okay, so that's a good recipe for R. However, R may have negative entries. On its main diagonal. If it does, if so, then here's what you do. Then you take the first negative entry along its main diagonal, and you make that column of Q its opposite. If so, take the first such entry and multiply that column of Q by -1. And so then recalculate. Recalculate Q transpose A. Repeat until all entries along the main diagonal are positive. And once you have that, then you're done. So let's give this a try. So let's try this actually with the matrix that we were just talking about before. So example, let's say that A is equal to, and so this will be the same matrix from before, 1, 2, 0, -3. 1, 1, 1, -1. 0, 2, 1, 3. Okay. So here we already have a first draft of Q. So from above, Q is equal to, we already calculated this, so our first vector was 1 over root 14. 2 over root 14. 0. Negative 3 over root 14. This is our first draft of Q. And then we're going to have over here, for the second one, U2, which is 4 over root 70. 1 over root 70. 7 over root 70. 2 over root 70. And then lastly, we're going to have negative 1/6, 5/6, negative 1/6, and 1/2. Okay. Now what we're going to do is, just to make things easier, is we will use technology to get Q transpose A. And that'll give us our first draft of R. So let's try that. So first off here, I have just entered in all the values for the matrix A, and then I can use like the little store button right here. So this is for TI-89. And then alpha A, so that's going to store the value as A. Doesn't have to be capitalized, and then just quick check, make sure there wasn't a typo. Okay, well if that's the case, then on to Q. And now I have just entered in all of the pieces for Q, and then I will do store, and then alpha and Q to store it as that. Notice, by the way, my original version was in this form, the same way we wrote it, but the calculator, as soon as I entered it, like automatically, it couldn't help itself. It rationalized all the denominators. These are all the same number, they just look different when the denominators are rationalized, so nothing to be concerned about, it's just the calculator's habit of rationalizing denominators. Now, if I want to confirm, by the way, that my Q does what it's supposed to do, Q transpose times Q should just equal the identity. Now, let's just check that. So you do alpha Q. Now to do a transpose, if you go to math, so second and math down here, and you do the matrix option for the very first one, there is the transpose, and so you put that in and it automatically gives a little superscript of T, and then you do that times Q, and this, if Q really is an orthogonal matrix, this should equal the identity. Sure enough, so it does. Alright, well in that case we'll do Q times A, so alpha for alphabetical, and then A, and what we have is this. So we have, and we don't care about the fact that the denominator got rationalized, none of our business really, so we'll just let it stay rationalized. So root 14, 3 root 14 over 7, negative 5 root 14 over 14, 0 root 70 over 7, 3 times root 70 over 14, 0, 0, 3. Now, in this, it actually did not happen that any of these ended up being negative. However, if any of them had been, which will usually only happen if you have gone a little bit off script in finding your Q, but if any of these had been negative, I would have changed my Q by multiplying that column by -1 in order to get the in order to adjust the R. And I would have worked my way from left to right. The very first entry here that had a negative entry on the main diagonal, say if it had been the very first one, then I would have just multiplied the whole first column of Q by -1 and changed it. Okay, but that's kind of an exceptional thing. It's a little bit of a technicality. It's not the important part about the R. The important part about R is that it is upper triangular. The R here stands for right, which is because all the entries are on the right of the main diagonal. As for Q, Q is a kind of standard letter for an orthogonal real-valued matrix. A common letter if it's a complex real-valued orthogonal matrix, also called unitary, would be U, but Q is what we typically use here. Okay. Well, now let's discuss what the point of a QR factorization is. So note, if A equals QR as above, so Q is orthonormal, or has orthonormal columns, R is upper triangular with all positive entries along its main diagonal. If A equals QR as above, then for one thing, R being triangular means that it will be invertible. Then R is invertible, and then A transpose A is going to be equal to, so Q R transpose times Q R, which is actually then just going to equal R transpose Q transpose Q and R, but here this makes the identity, so this is equal to just RT R, which is invertible if R is invertible. So that means that A transpose A is invertible. Now we'll see what the use of this is in the next section when we start talking about least squares approximation. But until then, thank you for joining me for this episode of Math 261. I'll see you next time. Bye.